Welcome to The Explainer. Today, we're diving deep into the hidden world of microchip design. We're going to uncover the invisible, super high-stakes process that makes sure the billion-transistor brain in your phone works perfectly right out of the box. Okay, let's start with a simple idea. Imagine you're designing a massive skyscraper. Would you just build it without testing the blueprint first? Of course not, right? You run simulations, test every single beam. You'd want to know how it holds up in an earthquake. To do anything else would be, well, just asking for a catastrophe. Well, that exact same logic applies to the tiny, unbelievably complex chips that power pretty much everything in our world. A single tiny flaw in that digital blueprint could make millions of chips completely useless. We're talking about a mistake that could cost a fortune and delay products for months or even years. And that is where something called functional verification comes in. It's the official name for this whole testing phase, and its entire purpose is to make absolutely sure that the digital model of a chip does exactly what it's supposed to do long before anyone even thinks about actually manufacturing it. So how in the world do you test a chip that doesn't even exist yet? I mean, you can't hold it in your hand. Well, the answer is you build a virtual proving ground. It's a complete digital world designed specifically to put that blueprint through its paces. Probably the best way to picture this whole thing is like a high-tech crash test facility. But, instead of smashing cars into walls, we're throwing every digital scenario you can imagine at a chip's design, just to see if we can break it. And in our virtual facility, the first thing you need is, well, the car. In our world, this is the design under verification, or DUV for short. This is the actual hardware model, the digital blueprint that we're trying to test. Now, the entire virtual environment itself, the test track, the obstacles, the sensors, the whole shebang, that's what we call the test bench. It's the complete framework that we build just to run all of these tests. So inside this test bench, you've got a component called a stimulus generator. Its job is to create all of the test inputs, the stimuli. These are basically our crash conditions: a head-on collision, a side impact, slamming on the brakes, everything designed to stress the DUV. And of course, after the test, you need to see what happened. That's the job of the response monitor. It watches everything the DUV does, acting like a whole bunch of high-speed cameras and sensors, checking if the design behaved exactly the way it was supposed to. So when you put it all together, the flow is actually pretty simple. The stimulus generator sends a signal, the design under verification does its thing and computes a response, and then the response monitor checks if that response was correct. And this little loop? It repeats thousands, sometimes millions, or even billions of times. Okay, so all of this might sound a little abstract. Let's bring it down to earth with a really simple example. Let's forget about a crazy, complex processor for a minute. We're going to look at one of the most basic building blocks in all of digital electronics, a simple 4-bit counter. Its only job is to get a pulse and then count up, one step at a time. And this is a perfect way to see that separation of tasks we were talking about. The counter's job is super simple. See a clock pulse, add 1 to the count. The test bench's job is to actually provide that pulse, that's the stimulus, and then watch the output to make absolutely sure it's counting correctly. So the response monitor would be looking for a progression that looks just like this. At time 0, the count is 0. After the first clock pulse, say at 100 time units, the count better be 1. At 200, it should be 2, and so on. If the monitor sees this exact sequence, great, the test passes. But hang on, this super simple example brings up a huge, critical question. A counter is one thing, but for a real chip, with billions of parts and literally trillions of possible states, how do you ever know you've tested enough? How can you be confident the design is really, truly flawless? Well, the key thing to realize is that quality beats quantity. Just creating tons and tons of random tests isn't going to cut it. You need what they call a diversified set of tests. I mean, testing the same simple function over and over again is a complete waste of time. So to actually measure the quality and the thoroughness of all this testing, engineers rely on 2 really powerful metrics. They're called code coverage and functional coverage, and they answer 2 very different but equally important questions. Here's the best way to think about it. Code coverage asks a very literal question. Of all the lines of code that I wrote for this chip's blueprint, did my tests actually run every single one of them? But functional coverage asks a much higher level question. It asks, of all the features that I promised this chip would have, did I actually test that every single one of them works correctly? Now, each one of these has a catch. Code coverage is pretty easy to measure automatically, but it has a huge blind spot. It can't tell you if you forgot to write the code for a feature in the first place. I mean, think about it. An empty file has 0 lines of code to test, so technically it has 100% code coverage. Functional coverage, on the other hand, can find those missing features, but it's a much more manual process. It requires engineers to basically create a detailed checklist of every feature that needs to be tested. So what's the goal here? Well, for anything mission critical, we're talking peacemakers, flight control systems, the huge processors and data centers, engineers are pushing to get as close to 100% on both of these metrics as they possibly can. It's this exhaustive effort to hunt down every single potential bug before it can cause a real-world disaster. So when you step back and look at the big picture, you see that functional verification is this massive, invisible, and incredibly painstaking process. It's like the silent guardian that builds the foundation of reliability for all the modern tech we totally take for granted. So I'll leave you with this thought. The next time your phone or your computer or your car just works without a single glitch, take a second to remember the immense hidden world of virtual crash tests and digital blueprints that made that seamless experience possible.